Welcome back, everyone. Before we get to section 2.2, a quick note about the anti-symmetric matrix or skew symmetric. Okay, neither one of these are examples, but I wanted to show you something that would be. If I took a generic matrix like A, B, C, D, E, F, G, H, I, and we call that matrix A. And I wanted to compute A transpose, I would get A, B, C, D, E, F, G, H, I. Okay, where all the rows of A are now the columns of A transpose. And negative A would be the opposite of all the entries in A. So minus A, minus B, minus C, minus D, E, and F, minus G, H, and I. Now, skew symmetric means that A transpose is equal to negative A, which means we have to match these up component-wise. So the first thing to observe, if you look along the diagonal, is that minus A has to equal positive A, minus E has to equal positive E, and minus I has to equal negative I. Or minus I has to equal positive I. Well, that's only true of a certain number for each of those. That means A, E, and I have to be all the same number, 0. 0 is the only number that is equal to negative itself. So when we look at a skew symmetric matrix, only the ones that have 0 along the diagonal are candidates. Okay, what about everything else? Okay, well, D has to be equal to minus B. G has to be equal to minus C. And H has to be equal to minus F. And we can compare that. I mean, here we have B is equal to minus D, C is equal to minus G, F is equal to minus H. That's just moving the negatives over to the other sides. So if we call B1, C2, and H3, since D is equal to negative B, okay, then this would be negative 1. G would be equal to minus C, this would be minus 2, and this would be minus 3. So this right here is our example of a skew symmetric matrix. Because if I look at A transpose, make all these rows columns, 0, 1, 2, negative 1, 0, 3, negative 2, negative 3, 0. And you look at the negative of A, that means 0, negative 1, negative 2. 1, 0, negative 3. And 2, 3, 0. You would see that the matrix for negative A is equal to the same matrix that you'd get if you took the transpose of A. So, in other words, a skew symmetric matrix is 0 along the diagonal, and the entries in the upper triangle are the opposite sign as the entries in the lower triangle. All right, so with that said, let's run into section 2.2. Where'd it go? There we go. A little bit more vocabulary in this section, so the video will kind of go fast. Matrix addition requires each matrix in the sum to be the same size. Okay, so for example, if you have the matrix 1, 0, 2, 4, and you added to it 3, 4, negative 1, 2, you add each entry component-wise. So 1 and 3 is 4. 2 and negative 1 is 1, 0 and 4 is 4, 4 and 2 is 6. Okay, if you look at scalar multiplication, all you're doing is multiplying each component of the matrix by the scalar out in front. So that's 30, 15, 12, and -3. Matrix multiplication is a little bit more complicated than addition or scalar multiplication. Okay, it requires the first matrix have the same number of columns as the second has rows. So that means if A is a 3 by 2 matrix and B is a 2 by 1 matrix, then that product makes sense, but B times A, where B is a 2 by 1 and A is a 3 by 2, doesn't make sense. So if you just write out the rows and columns underneath each matrix, so A is 3 by 2, 3 rows, 2 columns, B is 2 rows, 1 column, the number of columns in A has to be the same as the number of rows in B. And the resultant matrix is the other numbers. Will be have 3 rows and 1 column. Here you can see that the number of columns of B doesn't match the number of rows of A, so that product doesn't make sense. One thing to note, matrix multiplication is associative. That means if you have a product of 3 matrices, A, B, and C, you can multiply A and B first and then multiply by C, or you can multiply B and C first and then multiply by A, but not commutative. That means A times B is different than B times A. In fact, in this case, B times A doesn't make sense. Now, if we look at how the product works, okay, I've circled the component -7 in the resultant matrix. Okay, first off, let's talk about what this is we're looking at. This has, 3 rows in it and 4 columns. So this is a 3 by 4 matrix. This has 4 columns, or 4 rows and 2 columns. That's a 4 by 2 matrix. We verify that the number of columns in the first matrix matches the number of rows in the second matrix, so the product does make sense. What you're left with is a resultant matrix that is 3 rows and 2 columns. So this is a 3 by 2 matrix. This element right here, -7, is in row 2, column 1. So row 2, column 1. Okay, to come up with -7, you look at row 2 of the first matrix, column 1 of the second matrix. So I've kind of highlighted or arrowed your attention to each of the relevant pieces. Okay, and so how do you come up with -7? Well, you multiply entry by entry. 2 times 1 is 2. 1 times -1 is -1. 5 times 2 is 10. And -6 times 3 is -18. And at that point, you sum each of those products. So you get this to be 2 minus 1 plus 10 minus 18. So that's 11 minus 18. That's where you get your -7. Okay. We'll do one more just to kind of reinforce where this is coming from. Let's look at the 6 down here. Okay, so that's what? It's row 3, column 2. Row 3, column 2. Okay, so row 3, column 2, 3 times -2 is -6. 2 times 3 is +6. 0 times 4 is 0. 1 times 6 is 6. Add that together, you get to be 6, and that's why that entry is 6. Okay, and you do the same thing for all the other entries in the resultant matrix. I'm not going to do it because this is something that you've already been exposed to, and I really don't want to waste your time. But if you're having problems with it, again, feel free to stop by office hours, and we can talk about it. Okay, so that's first page. What about next? The identity matrix. The identity matrix is a diagonal matrix. Remember what diagonal means? That means the upper and lower triangular entries are all 0 with 1s along the diagonal. Okay. We identify the letter I to represent the identity of a matrix. We let the letter I to represent the identity matrix. Okay, the size of the matrix is determined usually in the context of the problem. So sometimes I can be a 2 by 2 matrix with entries 1, 0, 0, 1. And sometimes it's a 4 by 4 matrix with 1s along the diagonal and 0 everywhere else. The neat property about the identity matrix is that when you multiply it by a square matrix of the same size, you get the other matrix. So if I take 1, 2, 3, 4, 5, 6, 7, 8, 9, multiply it by the identity matrix, you get 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, out of it. So it's the matrix under multiplication that does not change what it's being multiplied by. A couple notes that are in the book. Okay, A transpose. Okay, the following are true about A transpose. A transpose transpose is equal to A. Because remember, A transpose means you take all the rows, make them columns. Well, you take the transpose of that, and all those columns are now rows, and you've reverted back to the original matrix A. If you look at taking the transpose of a sum, that's the same as transposing both A and B and then adding them together. And if you look at taking A times B and taking the transpose of the resultant matrix, that's the same as B transpose A transpose. So, in other words, multiply A and B together and take its transpose. That's the same as taking the transpose of B and the transpose of A and multiplying those together. Okay. So those are the highlights from section 2.2. Okay. Again, there's some gaps that you can fill in as you work through problems. It's not necessary that we do an example for every type of problem, but if you do come across something that you find confusing, by all means, feel free to stop in by office hours or send me an email. Section 2.3. Okay. This is where we're starting to get into I don't want to say that anything we haven't done is important, but the material that is essential for future success. Okay. So I'm going to give you a system of equations. There's 3 equations and 3 unknowns here. Okay. We get to write this system as a matrix equation. So that means we're going to take 2 matrices, multiply them together, and get a third matrix. Okay? So that third matrix is a 3 by 1 matrix. Okay? With entries 4, 7, and 0. Okay? What do I have to multiply by to get a 3 by 1 matrix? Well, the first matrix in the product has to have 3 rows to it. The last matrix in the product has to have 1 column to it. So it's got to be a 3 by something times a 1 by something. Okay, in this case, because you can see that there's 3 equations and 3 unknowns, the number of columns of matrix 1 is going to be 3. The number of rows of matrix 2 is going to be 3. Okay. Now, what goes in here? Okay, I'm just going to jump to the answer without making you discover it. The unknowns go in the 3 by 1 matrix, so that's x1, x2, and x3. And the coefficients on each of the unknowns go in the 3 by 3 matrix. So that's 2, 5, 3, 1, negative 1, 4, 6, 2, 1. and you should check your work. Okay, so let's take an example. So let's multiply row 2 times column 1. So row 2 times column 1 will give me 7, okay, because that's row 2, column 1 of the resultant matrix. So if I multiply these out, I'll keep it in red. Component-wise, I get 1x1 minus 1x2 plus 4x3. And because the thing that's on the left is the same as the thing that's on the right, that generates 7, because that's row 2, column 1 of the resultant matrix. So is this thing that I wrote down in red the same as the information given to me? Absolutely. 1x1 minus 1x2 plus 4x3 is 7. And the same works for rows or entries 1, column 1, and entry row 3, column 3. So that makes it nice and neat. I mean, you can take a system of equations and write it as a matrix equation very quickly, in, less than 30 seconds. Next page. So what we just did, writing a matrix equation, can be represented generically, okay, by the symbols A, which is representing matrix, times X, which is representing an unknown matrix, okay, a matrix with all of our unknowns, is equal to B. That's our resultant matrix. Okay, again, because if I take A, which is a 3 by 3 matrix, multiply it by this 3 by 1 matrix, what I end up getting is 2x1 plus 5x2 plus 3x3, multiplying each one of these component-wise. That's how I get the top line. 1x1 minus 1x2 plus 4x3, and 6x1 plus 2x2 plus 1x3. Okay. So if you don't see where we're going with this, we are going to be using matrix equations to solve systems of equations. Now, a homogeneous system of equations is of the form AX equals 0. That is where the resultant matrix is the 0 matrix. Okay. Now, the example that we just looked at, okay, this is not a homogeneous system, because though the resultant matrix has a 0 in it, it's not the 0 matrix. Okay. Instead, this is an inhomogeneous system because it's of the form AX equals B, where B is not the 0 matrix. A consistent system has at least one solution, whereas an inconsistent system has no solutions. Okay, so for example, if we look at 1, 2, 2, 4 times x1, x2 equals 5, 6, what system of equations are we looking at? Okay, we're looking at the system x1 plus 2x2 equals 5, and 2x1 plus 4x2 equals 6. So this is the system of equations that we're trying to solve. Okay. Well, first off, is the system homogeneous or not? And the answer is it's not, because the resultant matrix is not the 0 matrix. Okay, so this is not a homogeneous system. We can see that by inspection. Now, is this a consistent system or not? We can't answer that without actually trying to solve the system. Okay, so use any of the techniques that you're familiar with. Okay, what I will do is I will multiply row 1 times the scalar 2. So that gives me 2x1 plus 4x2 is equal to 10. 2x1 plus 4x2 is equal to 6. So if you look at this, you can see right away the left-hand side is equal to 10. That same left-hand side is equal to 6. And since 10 is not equal to 6, the system is inconsistent. Okay, it does not have a solution. Now, what would it take for this system to be consistent? Okay, well, it would have to have at least one solution. So there's different ways of having at least one solution. Okay, consider the following. What would happen if we had made 6, replace 6 with the number 10? Okay, we'd have 1, 2, 2, 4, x1, x2. That would make this 2x1 plus 4x2 is equal to 10. We'd multiply the top row by 2. You get 2x1 plus 4x2 equals 10. The second row would be 2x1 plus 4x2 equals 10. And now we'd have the equation 10 equals 10, which is true and would make the system consistent. Very good. Can you think of another way of making the system consistent? Here's a hint. Look at the relationship between the rows of the coefficient matrix. We usually refer to this as the matrix A. Okay, and this is X, the unknown vector or matrix, and B is the resultant. Okay, look at the relationship between the rows of A, 1, 2, and 2, 4. Okay, it's not a coincidence that the row 2 is twice row 1. Had we changed, well, I'll pose this as a question for you to solve. What would happen if we had changed the coefficient matrix and instead of a 4 wrote that as a 3? So for keeping track of all the changes, you would be looking at 1, 2, 2, 3 times x1, x2 equals 5, 6. It would still be a non-homogeneous system, okay, because the resultant matrix isn't 0. But would it be consistent or not? Okay, I'll leave that for you to answer. Okay, what would happen had we changed this to anything but a 4? Anything but a scalar multiple of row 1. Okay, and once you know the answer to that question, you'll be taking a big step towards understanding the relationship between the A matrix and whether a system is consistent or inconsistent. And I'm not going to leave this as a cliffhanger. I will tell you the relationship in future videos. Okay, but I'm sort of trying to encourage you to think ahead as to what the relationship is between A and the system of equations. Okay, so section 2.4 comes next. I hope you're having a good day.